In this video, I will go over the homework that follows the lectures 11.1 and 11.2. And as always, I hope you watched all these lectures, as I will be making references to the material presented in those lectures, assuming that you have familiarized yourself with all that material. And the topic is integrating rational functions, and the idea is very, very simple. We're going to build a library of what we would call a basic integrals of rational functions, and then we're going to use the partial fractional decomposition to decompose a rational function into a sum or difference of basic rational functions, and then we're going to be using the knowledge of those basic rational functions to find the antiderivative. So that's the simple idea, and let's go ahead and jump right into the homework. And the first question also gives us a hint, but even without a hint, we understand that this rational function is improper. Improper meaning it is the degree of the polynomial in the numerator is not less than the degree of the polynomial in the denominator. So that means we can use long division to write it in quotient form, which essentially will break it down and will allow us to reevaluate the integral. So again, the long division is something that we have learned to do long time ago, and I'm not going to try to teach you how to do long division here, so I'm just going to use technology to help us with this simple task. And here I'm missing a parenthesis, so you have to make sure you enter your input correctly. Now, one of the alternative forms here will be right here. This is the quotient form. So this integral by long division can be broken down into, or rather rewritten like this. Now we can use the linearity of integrals and write it like this. And now we approach both of these integrals separately. So the first one is just x plus c, but the second one, to do the second one, we're going to do substitution. And again, let's say, how do you know how to do this problem? We actually learned it in this lecture right over here. We probably did even a much harder one. So it's a linear substitution problem. We're going to set t equals 2x minus 4, so that dt is equal to dx. And now this integral becomes, the first part is x. We're just going to put plus c at the very end, so this becomes x. And this integral becomes 7 integral of 1 over t dt, which is ln absolute value of t, but t is x plus 4, so x minus 4 rather. So this will be the final answer. So let's go ahead and type that up. And we got that right. Here's another problem, similar idea. Even without the hint, we would have recognized that this is an improper rational function, meaning that the first step is to perform long division. So because long division is not a calculus task, I'm just going to use Wolfram alpha. So here's my rational function, here's my numerator, here's my denominator, and we're going to look for one of the alternative forms right over here. So we're gonna write it as the quotient plus the remainder divided by the divisor. And the idea is that now it's definitely a simpler integral. We're going to use the linearity of integrals and split it into two. And now for the second one, as I'm writing it, I'm recognizing that it's one of the basic rational functions. And we covered it in this lecture. So I'm looking at the denominator. It's an irreducible quadratic trinomial. And this problem, the way it looks here, it fits this, it fits this template right over here, right? Except, let me just go all the way back. So this is kind of what the solution is going to look like. Do we have an example here? No, we have a complicated example. This is actually what we have, kind of, right? Yeah, this is what we have, right? So this is what we have, except that we have 2 in the numerator. So I'm going to take out the 2. So now I have x plus 1/2. And in the denominator, I have x squared plus x plus 1. But it doesn't help us to have the denominator written in standard form, so we need to complete the square. So knowing that, I'm not even going to write the denominator out. I'm actually going to start completing the square. And to complete the square, we're going to add and subtract half of the coefficient of x squared. So we're going to add and subtract half of the coefficient squared. So we're going to add 1/4 and subtract 1/4. And now what we have here is just x plus 1/2 squared. And what we have here is just 3/4. So this whole process of manipulating this expression is called completing the square, and it's not a calculus task. So we should be able to complete this task somewhere on a scratch paper. So let me remove this from the integral, and then just put this as a thought bubble right over here. And in the denominator, I'm just going to write the result. So we have x plus 1/2 squared plus 3/4 dx. And again, I'm just following this this template. And in the template, the substitution t equals x plus 1/2 suggested. And in this case, dt will be equal to dx. And continuing with this whole integral, what do we have? The first part of this integral is just 5x. But the second part will be 2. And now we perform the substitution. So we have t over t squared plus 3/4. I wanted to write dx, but dx is dt. And And this now becomes a much simpler problem. And if you don't recognize the way of handling this particular problem, then just watch this example. Let's see if it's this. It's not even this one. It's much simpler. This is the problem that we have, right? So we can just follow this as a template. The second substitution that we're going to do to handle this integral substitution is we're going to set the new variable, let's say s, to be equal to t squared plus 3/4. So that ds will be equal to 2t dt, and half of ds will be t dt, which will take care of this part of the pattern. And now plugging everything in and continuing with the main problem, we still have that 5x, it didn't go anywhere. We have 2, and we have integral now of what do we have? In the denominator we have s, and here we have dt, but dt is combined with this t, so it's just 1/2 of ds. So this 1/2 and this 2 are gone. And now we can write the answer. So we have ln of absolute value of s plus c, but s is t squared plus 3/4. And let's not forget what t stands for. T stands for x plus 1/2. And the last thing here to notice is that x plus 1/2 squared plus 3/4 is actually our denominator, which is x squared plus x plus 1. And that's the final answer. And in this case, the absolute value is not necessary because irreducible quadratic trinomials are always positive. All right. We have another very similar problem. So this will be number 3. Integral of 3x squared plus 11x plus 18 divided by x squared plus 3x plus 5. We notice that it's an improper rational function, so we're going to perform long division to write it in quotient form. This will inevitably make the integral much simpler. So here's the quotient form. We have 3 right here. This is the alternative form that I'm looking at. 3 plus 2x plus 3 dividing by x squared plus 3x plus 5. Now, Newton made it so there is a pattern that you can take advantage of. And just do a the following substitution. But in general, you wouldn't count on this pattern, and you would do this type of problems the way I showed you in the previous example. But the substitution here that actually does the trick is the entire denominator. Just set it equal to t, so then dt will be equal to 2x plus 3 dx, and as you can see, that's exactly what we have in the numerator. And now we continue with this integral. So the first integral is just 3x, and the second integral just becomes an integral of 1 over t dt. So we have 3x plus ln absolute value of t, and finally, instead of absolute value of t, we put absolute value of x squared plus 3x plus 5. But like I said, in general, these coefficients 2x, these coefficients may not be 2 and 3, they could be something else, and then when you don't see this pattern, what do? Well, then you have to do it this way, the way I demonstrated, I showed you earlier. So here's the answer for this question. We have 3x plus ln absolute value. And again, there is no need for absolute value here, because this is a reducible quadratic expression, which, when evaluated for any values of x, produces a positive output. Another very similar problem. So let's do the long division. Here's the result. Here's the quotient form. You should be able to identify it among many other ways of writing this rational function. And again, this is a irreducible trinomial in the denominator, and we proceed with first splitting the integral into 2, and second we're going to do the same substitution as we did before. T will be equal to x squared plus x plus 3, and dt will be 2x plus 1 dx. So this problem now becomes 2x plus integral of 1 over t dt, which is now this, which is now this. And I'm not even putting the absolute value here, because irreducible quadratic expressions evaluated at any number always give you a positive output when the leading coefficient is greater than 1. So here's the answer. Number 5. So what we do with these rational functions is pretty much determined by the appearance of the rational function. So we don't even need those hints. So because it's improper, we need to use the long division to simplify it. That's a must. The partial fraction decomposition only works on proper fractions. So we can't even think of partial fraction decomposition until we write the function in quotient form or make it proper somehow. So the quotient form here is actually, it's interesting here. It doesn't give me the quotient, so I'm going to be very specific then. Divide this by this. Interesting. Interesting. It doesn't. I might have to do this by hand, the long division. It understands it as a rational function, but it, for some reason, it just refuses to do the division. Interesting. Okay, well, that's why we learn how to do the division by hand. So if you remember, actually, I may not remember myself how to do this long division. Let me see. So we write it like this. Here goes the coefficient 3. Is that right? I multiply, so I have 3x squared minus 12. Subtract, so I have 3x minus 7 plus 12. It's plus 5. And that's it. So this is my quotient. This is my divisor. This is my remainder. So the and actually, since this is not calculus, we're gonna put this in a thought bubble right around here. So this is our thought bubble. But what we achieved by doing this long division is that now we have a simpler problem. So the 3 can be separated from the rest of the problem using the linearity property of integrals. And now, how do we identify the next step is we look at the denominator. And denominator here happened to be a reducible quadratic binomial. So that means we have to proceed with factoring it. So instead of x squared minus 4, I'm going to write what it stands, or not what it stands for, but like its actual prime factorization. Not prime factorization, just factorization. So here I use the difference of squares formula. And this is what triggers the partial fraction decomposition. So according to the partial fraction decomposition theorem, the first integral is not even a problem, right? So that's just 3x. But according to the partial fraction decomposition, this integral right over here, or this rational function right over here, can be decomposed into this. That's what the partial fraction decomposition theorem tells us. So finding these coefficients a and b is not a calculus task. So this is not something that we learn to do in calculus. This is something that we learn to do in college algebra class or pre-calculus. So I'm not going to bother with doing it by hand. It usually takes a certain number of steps and results in a system of equations that you have to solve, which may take 30-40 minutes. So we're just going to use Wolfram Alpha to perform this algebraic task, so we can just focus on the integration. And here you can see Wolfram Alpha calls it partial fraction expansion. So according to the partial fraction decomposition, the coefficient a is what's around x minus 2, so a is equal to 11/4, b is equal to 1/4. That's what we learn from the partial fraction decomposition. So after we apply the partial fraction decomposition, we now have the following problem. We have 11/4 of x minus 2 plus 1/4 of x plus 2 dx. And these are very simple integrals. You can do them by simple linear substitution. I'm just going to write the answer. And that's it, right? So once you remove the heavy algebra stuff, like completing the square, partial fraction decomposition, integrating rational functions, it's pretty straightforward process. So you shouldn't be getting lost as you're performing integration of rational functions. I'm not saying that partial fraction decomposition is easy or completing the square is easy, but the idea behind integrating rational functions is easy and straightforward. All right, we got this right. Of course, if you look at the Newton solution, it does do everything by hand, but we don't need to. So next problem. So here we have a proper fraction, so we don't need to do long division. So we can apply partial fraction decomposition right away. And in order for us to do that, we have to factor out the denominator. This is how we know we can apply the partial fraction decomposition, because denominator is reducible and it can be written as a product of, in this case, two distinct linear terms. So according to the partial fraction decomposition, this can be broken down into this. Now, to find A and B, we're going to use the partial fraction decomposition. Because it's not an algebraic, rather, it's not a calculus task, I'm going to use technology, just so we can focus on calculus here. But if you're doing this by hand, it may take you a couple, if not more than a couple minutes. Let me see here. I'm missing a parenthesis here. This is the partial fraction expansion, so we can see that A is equal to 2/3, B is equal to -5/3. And this integral therefore becomes 2/3 over x plus -5/3 over x minus 3. And we know how to integrate each one of them. So the first one is 2/3 ln of absolute value of x. The second one is -5/3 ln of x minus 3. Six, 7. So the denominator is factored out. The rational function is in proper form, so we have to use the partial fraction decomposition theorem, according to which this will be equal to some fraction with the denominator x, another fraction with denominator x squared, and then another fraction with denominator 3x plus 4. That's the partial fraction decomposition theorem. Now, according to the partial fraction decomposition process, we should be able to find A, B, and C. Because this is not a calculus task, I'm going to delegate it to Wolfram Alpha. And Wolfram Alpha will tell me exactly what the partial fraction decomposition is. So A is -9/8. So I'm reading it from over here. So this is the what A should be set equal to fit this pattern. B is 3/2, and C is 27/8. So my integral now becomes, it actually becomes three separate integrals. So the first integral will be -9/8 integral of 1/x dx. My second integral will be 3/2 integral of 1/x squared dx. And the last one will be plus 27/8 integral of 1/x 3x plus 4 dx. Each one of these integrals is a well-known, so you shouldn't have a problem doing this manually. This is just ln of absolute value of x. This will be your -1 over x. This one will be 27 over 8 times 1/3 ln of absolute value of 3x plus 4. And of course we have plus c at the end. So let's go ahead and type the answer. Notice how here I am putting absolute values, because the expression inside may be positive, may be negative for different values of x. I forgot what problem number this was. Number 8. We have something that looks scary. It looks scary only from the algebraic point of view. If you're doing algebra by hand, then sure. But to us in calculus, what matters right now is that this rational function is proper, meaning this is less than the sum of this. So we compare the degrees of the polynomials in the numerator and the denominator. Now, because it's proper, and I would assume it's reduced, hopefully, right? And if it's reduced, then we have to use the partial fraction decomposition, which will say that this rational function can be rewritten as the sum of this rational, but simple rational functions. So that's what the partial fraction decomposition theorem tells us. Now, it could be really tedious task of figuring out coefficients a, b, c, and d by hand, which I'm going to delegate to Wolfram Alpha. This one will be a real pain in the butt to do by hand. Let's see if Wolfram Alpha handled it. Let's also make sure we typed it correctly, which seemed to be the case. And if you look at the output here, we have partial fraction decomposition right over here. So my A is -1/6. My B is -25 over 14. Someone who has to do it by hand probably hates it, as it's very understandable. C is the coefficient of x, so we have to include that 21 from the denominator, so it's -1 over 21. And D is -30 over 21. So that's what we have, right? Again, this was algebra task, so we're not concerned with that. Now we got that out of the way. My integral becomes very simple. It is -1/6 over x plus -25 over 14 over x minus 2, plus here we have negative 1 over 21x minus 30 over 21 over x squared plus 3 dx. So this is actually 3 different integrals. So I'm going to actually break it down in 3 integrals. So we have negative 1/6 integral of 1 over x dx minus 25 over 4 integral of 1 over x minus 2 dx. And for this one, for the third one, I actually am going to check real quick on the which one is this? This is very similar to this problem. However, we have multiple things, so it's very similar to this problem. So let's check out how this problem was done. And it seems like splitting it into 2 was the right way. And that's what I'm going to do then. I'm going to split it actually into 4 integrals. So I'm going to have negative 121x over x squared plus 3 minus 30 over 21, which is 10 over 7. I reduced this by 3 of 1 over x squared plus 3, and we have dx over here. And we now ready to write the answer. So this is negative 1/6 ln absolute value of x. This is negative 25 over 4 ln of x minus 2. This one is, so again, I'm going to just write the answer, but you may want to actually work it out carefully by hand. The answer here will be 1, so we're going to have an extra 2 over here, so 1 over 42 ln of x squared plus 3. Check my work. And the last one will be, it's a pretty standard integral. Which you can find right here. It's pretty much at the very last step of this problem. So again, this is the pattern. In our case, we have, instead of 5, we have square root of 3. So the answer here will be 10 over 7. And we're going to have an extra square root of 3 over here. And we're going to have arctan of x over square root of 3. And of course, we're going to have plus c at the very end. You should be able to verify all these outputs manually. And if something is wrong, we are about to find out. So we have negative x ln of x minus 25 over 4 ln of x minus 2 minus 1 over 42 ln of x squared plus 3. So the parenthesis here, the absolute value here is not necessary. This one, you may be forced to simplify this, as usually we don't allow radicals in the denominator, but it's really not that big of a deal at this stage of the problem. And we got plus c. Oh yeah, I already see the typo. We have 25 over 14, but then 14 became 4 somehow. So this should be 14. I don't know if you noticed that as I was going through, but yeah, hopefully. Well, now I'm paranoid. If I don't get this one right, I'll have to redo it. So one way to check your answer is to actually scroll down in Wolfram Alpha and get this right here. And it seems like it's the same expression, just simplified in a different way. So I'm pretty confident that this time we got it right. So let's submit it again. Excellent progress. Now, if you look at the solution, probably absolute majority of this solution is algebra. Is you doing the partial fraction decomposition, and that goes on and on and on and on. So once you, like I said, once you get over that step, it's a pretty straightforward process. All right, let's move on. Now we have a problem in which integrating a rational function, it's just a step. It's not the entire solution, but a step. So let's take a look at this problem. And what we notice here is that if I arrange this substitution, so if I choose t to be tangent x, then dt is the secant squared x dx, and the original integral now simply becomes, and by the way, I can reduce all those 2's, so the secant squared x dx is now dt. 2 is gone, and in the denominator we have 2 t squared plus t. Now, what does it have to do with rational functions, you might ask? The answer is, it is a rational function, but now written in terms of t. So what we do next depends on whether it's factorable or not, and it's very easy to see that t can be factored. Now, that being a rational function means, and the denominator being factorable, means we can use the partial fraction decomposition theorem and decompose it into the following sum. And the coefficients a and b can be found using the partial fraction decomposition. And because it's not a calculus task, I'm going to delegate it again to Wolfram Alpha. And I'm going to do that by simply typing 1 over, and just make sure you type enough parentheses, 2t plus 1 times t. So partial fraction expansion is there. That means my b is equal to 1, and my a is equal to negative 2. So the final integral, not the final answer yet, but the integral is this. But I'm going to split it right away, so here's what we have. Now, these are very simple integrals. The first one will be negative ln of absolute value of 2t plus 1. The second one is just ln of absolute value of t. But remember, the original variable wasn't t, it was x. So we're going to simplify it further and write it out like this. That's the final answer. All right, continuing to the next problem. Very similar problem to what we just did. The first step is to probably clean up the integral and reduce all those extra 2's. They're just not necessary. Now, notice that the substitution that I'm about to introduce here, basically setting t equal to cosine of x, results in dt being sine of x dx. We have negative sign over here, meaning that the original integral now becomes negative 1 dt, and in the denominator we have 2t squared minus t. This, by the partial fraction decomposition theorem, can be decomposed into, well, first of all, how do I know I have to use the partial fraction decomposition theorem? Is that because the denominator is factorable. That's how we know we can use the partial fraction decomposition. If it's factorable, that means the original rational function can be decomposed into the sum of these two rational functions. And using the partial fraction decomposition method, we can find A and B. I, however, am going to delegate this task to computer. Make it useful. And looking at the partial fraction expansion, we can identify A to be 1 and B to be negative 2. And continuing now with the problem, so we have integral of 1 plus t. I can break this up right away. So we have minus 2 over 2t minus 1 dt. And these are very simple integrals, which we all should be able to do by hand. So we have ln of 2t minus 1 plus c. But instead of t, I'm going to write cosine of x. Plus c. And we are almost, hopefully, near the end. Let's do number 11. We have integral of 7x squared over x squared plus 3 squared dx. We recognize this as a rational function, which is proper. So we're going to be using the partial fraction decomposition, and based on the way the denominator looks, we're going to decompose this, or the partial fraction decomposition guarantees that the decomposition in the following form will exist. So it's going to be ax plus b over x squared plus 3 plus cx plus d over x squared plus 3 squared. Now we should be able to use the methods of partial fraction decomposition learned in algebra to identify a, b, c, and d. But as previously I've done, I'm going to delegate this task to technology. So I'm going to put this problem in Wolfram Alpha. 7x squared divided by x squared plus 3 squared. And you can see that the answer is actually nice because A is 0, C is 0, there are no x's in there, B is 7, and D is negative 21. This was partial fraction decomposition, which has nothing to do with calculus, it's algebra. So my integral is actually 7 divided by x squared plus 3 plus, or we can take that out and write it as minus 21 over x squared plus 3 squared. Now, these integrals are pretty standard. They're not easy, but they are standard, and we did learn how to integrate such functions in this lecture right over here. So for the first integral, we're basically just going to follow this example, not even this example right here, this template right over here. So the answer will be, actually, does it tell us the answer? Yeah, the answer is right there, right? It says 1 over a arc10 of x over a. This is the answer. So following this method, we can turn the first integral. Well, actually, let me take my time here to kind of rearrange things as well. So when I refer to the first integral, I mean this integral. So this problem is 7 over square root of 3 arc10 of x over square root of 3. That's the first one. Second one is 21 times, and what goes here is determined by the process, which is very similar to this problem. Except instead of 3, we have square root of 3. But we can follow this solution. I guess we can kind of hit the pause button here, like right over here. And we can kind of take this problem here to the bottom of the page. And again, just following these exact steps over here, my substitution is x is going to be square root of 3 tangent theta. So dx will be square root of 3 secant squared theta d theta. X squared plus 3 then will be 3 secant squared theta. So that, let's just remove everything like kind of from our view. So the problem now becomes integral of 1 over 3 secant squared theta squared, and dx will be square root of 3 secant squared theta d theta. Now we have a lot of reduction here. We're going to have square root of so secant squared cancel. We have secant squared in the denominator, which becomes cosine squared theta d theta. But we have 3 squared, which is 9, and in the denominator we have square root of 3, so we have square root of 3 over 9. Now cosine squared, we handle it the same way as always. use the half angle identity, but or rather reduction of power identity. So here we're going to have square root of 3 over 9, and instead of integral of cosine squared, I'm just going to write this answer. We have 1/2 theta plus 1/2 sine theta cosine theta plus c, and now we just have to figure out the triangle here, the reference triangle. It's we're going to use the fact that tangent theta is equal to x over square root of 3, which is opposite over adjacent. So x square root of 3, and hypotenuse will be square root of 3 plus x squared. So we're ready to find the answer. We're going to have, let's take out 1/2. We have theta, which is arctan of x over rad 3, plus sine theta, which is x over square root of 3 plus x squared, times cosine, which is square root of 3 over square root of 3 plus x squared, plus c. So that's what we're going to put inside of this parenthesis, except the plus c part. So we have square root of 3 over 18, and we can actually take that outside. And we have arctan of x over square root of 3 plus square root of 3 times x over x squared plus 3. And now we don't have to worry about that work. This is our final answer. So 7 over square root of 3 this one we have 21 square root of 3 divided by 18. We have arc 10 of x divided by square root of 3 plus x square root of 3 divided by x squared plus 3. It is possible that if you, I see what they did. If you forget about the knowledge of, I'm curious actually. Let's see. The answer is so simple that it leads me to think that there is a better way. And let's see, hopefully the next problem is similar so I can show you the better way. Let's see. Hopefully, right? Yeah, so let's see if the other way works here as well. So this was problem number 11. This is problem number 12. And ironically, this alternative approach actually doesn't require the partial fraction decomposition. We're just going to do what we did in the very last step. Remember this substitution? We're just going to try that substitution here right away. So we're going to let x to be square root of 2 tangent theta, so that dx is equal to square root of 2 secant squared theta d theta. X squared plus 2 will be square root of 2 secant. Actually, it's going to be squared, right? So we're not going to have square root there. So it's going to be 2 secant squared theta. And we may need a reference triangle. So tangent of theta is equal to x over radical 2. So we're going to draw the reference triangle like this. This is going to be x, this is going to be square root of 2, and this is going to be square root of 2 plus x squared. And now we're going to plug everything in. So we're going to have 7 x squared. Well, x squared is just 2 tangent squared theta. X squared plus 2 will be 2 secant squared theta, but we have it squared. And dx is square root of 2 secant squared theta d theta. Let's see if anything good comes out of this. Because that was kind of my hope. Secant squared cancels. We have, we also need to cancel like this 2, and in order to match this, canceling this 2. So what we have now outside is going to be 7 rad 2 over 2. Inside we still have tangent squared theta divided by secant squared theta d theta. But secant squared theta actually goes nicely into tangent squared theta. How so? That's your tangent squared theta. And dividing by secant is the same as multiplying by the reciprocal. So the cosine squared theta cancel. So this actual integral is just the integral of sine squared theta d theta. Meaning, how do we integrate sine squared theta d theta? We have to go to integrals of trigonometric functions, integrating powers of sine and cosine. Somewhere here there is the answer to this question. There you go, right over there. So integral of sine squared is just 1/2 of theta minus, and instead of sine of 2x, I'm going to write it 2 sine x cosine x using the double angle identity. So it's going to be 1/2 of sine theta cosine theta plus c, and the last step will be to take out the 2, and instead of theta we're going to write arc tan of x over radical 2, and instead of sine theta we're going to write x over square root of 2 plus x squared. And instead of cosine theta, we're going to write square root of 2 over square root of 2 plus x squared plus c. And this definitely looks much better than what we come up with in the previous problem. And this doesn't require the knowledge of partial fraction decomposition. So we're going to do 7 square root of 2 divided by 4. Inside of the parentheses, we're going to have arc10 of x over square root of 2 minus, we have x square root of 2 divided by square root of 2 plus, actually there is no square root of 2 over here, it's just x squared plus 2 plus c, and this is done. So this was a long homework, but it was for 2 lessons, 11.1 and 11.2. If you have any questions about using partial fraction decomposition or in general how to integrate a rational function, please feel free to reach out.